Hello students, this video is about the coefficient of determination, better known as R squared, which is used as a measure of how well a regression line fits a data set. So if you remember when we talked about correlation, we called correlation also R, lowercase r. So this is in fact related. This isn't an accident. In cases where the correlation is defined, the square of it is the same R squared measurement that we're going to talk about today. So what I want to talk about is what R squared is, kind of what it represents, and why it kind of gives us what it gives us. Okay? So if you look at this graph that I've drawn up here, what I've got is a line y equals mx plus b. This is that best fit line through a data set that we found last time. So remember we had a data set xi, yi. We had a line of best fit through it. And so what you can see on the graph, I've got a point up at the top here. This is a point xi, yi from my data set. I've got my means, x bar, y bar. So this is remember the mean of the x values, the mean of the y values. So this is kind of the center of the data set. And then I've got some things labeled on here. Okay, so if you think about it, when we create a predicted value, so when we create this y equals mx plus b, what it does is it gives us a prediction of where every xi should go to, right? So if you've got a particular value xi, it should be on this line if the data were completely linear. We're going to call that point right there xi, comma, yi hat. Okay, so we put a little hat over the yi. So that point is called xi, yi hat, so that's the predicted value. So up here we have the actual, here we have the predicted. And then down here we have the mean, the average value of the whole data set. Okay? So if you think about what this regression line does, it predicts that xi would go to this point. Xi actually goes to this point up here, xi, yi. And so what we're going to do is we're going to think about our, I don't know how well you can read this, so maybe I'll erase this and rewrite it. We're going to think about our regression as trying to explain the variation of how far yi is from the mean. Okay? So we would expect it to be some distance from the mean, right? We wouldn't expect all of our y values to be exactly on this center line because we think that it's linear, right? That it's tilted up in some way. Okay? But there's both explained variation and unexplained variation. So the regression line says that this distance here is explained, right? We expect it to be that far off from the mean. But then you also have this unexplained variation up here, okay? So this part is unexplained. The regression line doesn't predict it to be that far up, right? And so that's kind of error off of the regression line. Now this is unavoidable, right? We don't expect all of our points to be exactly on the regression line. So this unexplained error is going to be there. But ideally, if this data set really is very linear, that unexplained error should be very small, okay? And it should be a small percentage of the overall area. And that's where R squared comes from, okay? So if you think about these errors, this explained piece that error is yi hat minus y bar, right? That's the distance from the predicted value to the mean. The unexplained error is this part between yi and yi hat. And then if you think about the total distance, how far is yi from the mean itself? That's yi minus y hat. Okay? So each of these points is going to be some distance from the mean. What we would like, if this line were a really good fit, the unexplained part would be a small percentage of the amount of error, of the total distance that it is from the mean. The explained part would make up most of it. Okay? And so what we'd like is for the explained over total fraction, this ratio should be large. Most of the total distance from the mean to that point should be explained by the regression line. Okay? And this is the general principle. So r squared is going to basically be this quantity. Now, of course, we're not looking at a single point, right? We're looking at multiple points. So we need to add them all up. And then the other thing is if you think about going down to these points that are over here, right, where the data is less than the mean, we're going to get some negative values, okay? And so we're also going to square things. So what we're going to do is we're going to take all of these values, we're going to square them, and then we're going to add them all up. And we're going to give each of these names. So we're going to call SS, and in this book they use SS reg. So this is short for sum of squares. I don't have space to write this. This is short for sum of squares regression. So SS is sum of squares regression. I'll just say it and then write it down. So the sum of squares regression is going to be the sum of all the explained error okay? So that's the sum of squares regression. And we call it that because it's explained by the regression line. Okay? We also have the sum of squares SS res. So this is short for sum of squares residual. You'll also sometimes see this called sum of squares error. I think Excel calls it sum of squares error. So SS res is the unexplained error. So it's the sum of the yi minus yi hat. So the actual value minus the predicted value. And then we've got the sum of squares total. Okay, so this is residual and total. And that's the entire yi minus y bar squared. Okay? And so remember, just to kind of remind you of where these come from, just so that I've got all this on the board at one point. So yi is our data point. Y bar is the mean of all yi, so that's the average of the y values. And then yi hat is mxi plus b, right? That's the predicted value if you actually took xi and plugged it into the equation, where y equals mx plus b is our regression equation that we found earlier. Okay? So that's the terminology. Once we've got all of this, from these, we're going to define r squared to be the sum of squares regression divided by the sum of squares total. Okay? Now, assuming that our predicted values actually came from our regression line, that they're from the best possible regression line, this r squared will be a number between 0 and 1. So this is if y equals mx plus b is the line of best fit, then 0 is less than or equal to r squared is less than or equal to 1. And just like with correlation, the closer we are to 1, the better this is. But you can see that directly from this, right? So remember, the regression, SS regression, was the amount of the error that was explained by the regression line over the total, I shouldn't say error, the amount of the distance from the mean that was explained by the regression line divided by the total distance from the mean. And so if this ratio is large, if it's close to 1, that means almost all of the total distance from the mean is described by the regression line. And so that means the regression line fits really well. So the closer this is to 1, if this is exactly 1, it means all of the distance from the mean is described by the regression line. And so the data, it fits exactly on the line. Okay? So in the next video, we'll talk about using this in other scenarios, and we'll talk about kind of how to put this into Excel.